CAN frame structure consists of multiple bits which has start field. It indicates the beginning of a message with a dominant bit. Then message identifier defines the level of priority of the data protocol. If, let's say, two CAN nodes want to send their data simultaneously, then the CAN node with higher priority only gets the place. The information is transferred to the other CAN nodes in the data field. The CRC field is used for transfer fault detection. In acknowledgement field, also known as confirmation field, the receiver sends a signal to the transmitter that it has correctly received the data. And finally, end field marks the end of the data protocol. That's how a basic CAN frame looks like. We need to understand this frame structure in detail. So let's start. Bosch has come up with the CAN standard version 2.0 specification. This specification is further divided into two subdivisions, that is standard CAN and extended CAN frame. The standard CAN frame comes with 11-bit identifiers and it signals a rate of 125 kbps to 1 Mbps, whereas the extended CAN has 29-bit identifiers. Let's see the structure in detail with an example. We'll imagine a CAN data. This is a complete CAN frame structure, including stub bits, a correct CRC, and interframe spacing. There are two types of bits in this frame, dominant and recessive. Dominant bit means 0 and recessive bit means 1 on the CAN bus. Start of frame is the dominant bit. It indicates the beginning of a message. This bit helps to understand that someone had started the data transmission on the bus, or else the bus is set to an idle condition forever, which is a consistent recessive line. So this field marks the start of data protocol. A 3.75 volts, depending on used system, is provided over CAN high line and 1.25 volt is given at the CAN low line. So the differential voltage would be 2.5 volts. Once the frame is started, the identifier comes up. It is an 11-bit data considering a standard CAN frame which determines the priority of the message. If the numerical value is low, the priority of the message is greater. For example, if there are two devices that want to communicate having message IDs like 0x20 and 0x10, then 0x10 wins the arbitration because it comes first and has higher priority, so it gets the bus access earlier to transmit the message. We have already seen the concept of the bus arbitration in the video of I2C. You can check that video by clicking over here. The lower the value is, the higher will be the priority of the message. As stated earlier, depending on the standard being used, the length of the frames can be used in two formats: standard, which uses 11-bit arbitration ID, and extended, which uses 29-bit arbitration ID. Next is the remote transmission request. It determines whether the frame is a data frame or a remote frame. If the value is dominant bit, then it is a data frame. Otherwise, it is a remote frame. In this, the node requests data from another node. For example, in a WhatsApp group, we post a message with @ symbol to address a particular person with his phone number. This remote frame is used to request data from a particular device on the bus when needed, instead of allowing that device to consistently send the data and making the bus busy with unnecessary traffic. After that comes the control, also known as check field. It displays a number of items of information contained in the data field. This field allows any receiver to check whether it has received all the information transferred to it. It contains IDE, R0 and DLC. As we have seen earlier, there are two types of CAN frame formats, that is standard and extended CAN. Now the question arises, can we use same bus for standard and extended CAN? If yes, then how does the CAN node identify if the incoming packet is of extended CAN or standard CAN? That's where IDE plays an important role, which is known as identifier extension bit. If it is a single dominant bit, then it indicates that CAN identifier is transmitted without an extension. It is a CAN standard frame with the 11-bit identifier. The R0 bit is reserved for future purposes. We see this future purpose bit many times, but what it means is that there may be some features that can be added in future which can use this bit maintaining compatibility with the older devices. And after that, the data length code is a 4-bit code which specifies the amount of data submitted in terms of bytes. A message can be 8-bit, 16-bit, 32-bit or 64-bit wide. Based on the message byte length, this DLC changes. Next 8 bytes are the data field with application data. This is the actual useful information for receiving node. The limit for CAN data byte size is 8 byte only. We can't send more than 8 byte in a single frame. And after that, we have cyclic redundancy check, also known as safety field, which contains 15-bit code and recessive delimiter. The 16th bit after CRC bits is for a delimiter bit. Well, what is a delimiter? And why is it required? It basically provides the time for synchronization. Also serve a specific purpose in error detection, which is called form check. A form check basically checks whether the CAN frame sent or received is in a standard frame format. The CAN frame format must be maintained throughout the communication. The receiver checks for the delimiter bit after properly receiving the identifier and data. The delimiter bit must come at a predefined place so that the form of the CAN frame is maintained. If the receiver does not find the delimiter bits at a proper place, it generates a form error frame. It is just like die casting a melted Uru metal in order to make the storm breaker. The molten Uru metal is filled inside a die to take a form. If the die is not made properly, the storm breaker will cast in the wrong form and Thor will not have his axe. So before deinterpreting the data packet, these limiters are checked. If they are not maintained as per the protocol, then this is an invalid frame and the controller can ignore this frame or raise a form error. After that, if an error is detected, the receiver notifies the transmitter immediately. The transmitter then sends the data frame again. The receiver has to give an acknowledgement. There are 2 bits, an acknowledgement bit plus recessive delimiter bit. They are used to acknowledge the message that is being sent from one node to another. When the receiver receives the accurate message, then the receiver has to replace the upper bit with dominant bit, indicating successful message transmission. If the receiver keeps this logic high, the transmitting node retransmits the message according to arbitration. This acknowledgement is as same as acknowledgement mechanism in I2C, where other devices on the bus are telling the transmitter, hey, we got your message, or we got incorrect or no data, if they do not turn this bit to dominant bit. One of the crucial things to note here is that there won't be any acknowledgement if there is no other device on the bus, which makes it compulsory to have at least 2 devices on the communication line. After that, this end of frame includes 7 bits indicating the end of message frame. These 7 bits are usually recessive. This is the last possibility to indicate errors which lead to repeat transfer. And finally, interframe space is a 7-bit space, indicating the time that the controller has to move the received frame to the message buffer area correctly. It is a time given to the controller to process the packet. If you look closely inside the data frame, we can see the stub bits also. Well, that's how a whole CAN frame structure looks like. I have added all the references related to these circuits in the description. If you have any query, you can ask me in the comment section or email me. Hit the like button and subscribe to my channel. And finally, thank you so much for watching this video.